Good evening, everybody, and welcome. Especially welcome to our guest from Astropeiler. Now, if anybody has any observations they'd like to share later this evening, then do put a comment in the chat below, and we'll cue you in. I know for a fact that we have at least one astronomer eager to share results from last weekend. Our next resume, number 7 in this series, is on the tricky question of pulsars. Peter East will be presenting. Next Saturday, Saturday the 5th of June, it came round very fast, didn't it? We've got the second in our Python for Radio Astronomers series, and we'll be concentrating on reading SDRs with some Python code. Thank you very much, Rupert. The RAG 21 day conference in October 16th, put it in your diary. I'm really pleased that we can confirm that Professor Ian McCarty from Southampton University Physics and Astronomy Department is the keynote speaker in the morning, and he will be presenting the mysteries of X-ray cosmology. So as far as I know, that's something we've not covered in this series, that's for sure. However, this evening, I'm really pleased to introduce Wolfgang, known to you all, I'm sure. In fact, most of you probably knew Wolfgang before I did. The point that will remain in my mind with Wolfgang is he asked the question earlier this year, why do we do it? Why do we do it? And Wolfgang answered the question himself. Because it's fun. So with that thought in your mind, Wolfgang, I hand over to you this evening. Thank you.
Well, thanks very much. I'm very pleased to have you here tonight. I'm sitting in the control room of Astropeiler, and my plan for tonight is to tell you a bit about the observations that we are doing at the moment. What are the things that we are concentrating on? I've prepared a presentation on that. But of course, I also want to show you a bit around here and do maybe 2 demo observations. So I guess the starting point is that I share my screen. Do this one, and this one, and then hopefully.
Yes, that is working.
That is working. Okay. Yes. Just one remark, please don't be confused that I'm appearing several times in this meeting. That's because I'm logged in with 3 computers so that I can do certain things with switching cameras and also going to a demo computer. Anyway, so let me get started telling a bit about the current observations that we do. And for those of you who have never seen it, this is a bird's eye view of our campus with the 25-meter dish in the foreground. And hopefully you can see my cursor. This is where I'm sitting right now. It's on the 1st floor. That's where our control room is. And on this aerial view, you can also see a second instrument over here. That's a 10-meter dish, which we are mainly using for methanol at 12 gigahertz and for water Mesa observations at 22 gigahertz. We are presently working on the control system of that. So there's some work still to be done. It's a bit older, this picture. So by now, if it would be a recent picture, you would have number 1, the tree cutaway, and number 2, have a 2.3 meter dish located here. And there is a 3-meter dish behind this tree right here. And then you see 2, maybe 2 small dishes here This is a Ku band interferometer. So these are the instruments that we are using. I'm not going to tell about the other instruments, so I will concentrate on what we are doing with this here. Okay, in order to show you around a bit, I will stop this and share, hopefully. Okay, it seems to be working. So that's another camera where I'm sitting, but it's better to give you an overview. So I'll swing the camera around so that you have a first look at the control room. So there's a door, like every room has a door. That's where we come in. And then as we move over here, this is where we are typically sitting. At the moment, I have 2 laptops for this demo, but normally we will work on this big screen here. The reason I'm not using it, if I share that, you won't be able to see anything much. Then turning the camera further over. Let's see that I get that nicely arranged. So this is a control panel which we use for manual operation and just to turn things on. What I would like to point out is that you see 2 indicators here. These are the position indicators for azimuth and elevation, which are the original one from the 50s. We made them working again, and they're quite nice to get an overview. But of course, today we want to have computer control, and therefore we have, unfortunately, it's too light to be seen. This is the display of the position that we get from our high resolution angular encoders, and is displayed by a screen here. So it's showing the rectascension and declination of the target and the actual position. Another thing, let me get the camera maybe a bit closer here. This is a control monitor, and what you actually see here, hopefully you can see it. This is a 100 megahertz wide spectrum. So this is what we are receiving. That's a fairly sharp filter that cuts off everything else. And we use this monitor not for any research or trying to identify signals, just for keeping an eye on everything that's working fine. All right, then let me turn that bit over here. All right. Now, what we like to do is to keep a little bit of the old atmosphere, because this was built in the 50s, as you have already seen from the position indicator. So we have these old racks, but if you open that, everything in here is new. Let's see, how much can you actually see of that? Not too much, I guess, but anyway. This is what we call the machine control. That is everything that has to do with monitoring the motors, monitoring the brakes, the clutches, the gears, and so on. And on top of that, we have the actual astronomical control. This is a standard computer, which has special interfaces to our angular encoders. Okay, so just briefly for the motion of the instrument. Now let's go to the reception side of things. So I move the camera over here in front of the racks, and I go a little bit to the racks. Okay, I have to get the camera down a bit. So down here is actually where everything starts. We have the receiver up in the prime focus, and then we bring the signal down. It's a down converted signal from the L band down to 100 to 200 megahertz. So that's coming in here. And then this is a distribution amplifier unit. Essentially what we are doing is we're taking the two signals from the two polarizations and post amplify and split them up. So for each polarization, we have 4 outputs: 1, 2, 3, 4, one polarization, 1, 2, 3, 4 for the second polarization. And then it goes on to the analyzing instruments. Go a bit up here. Down here, this is a unit for continuum measurement, so that we measure the total power essentially. This is also a digital unit belonging to that. This is a spectrum analyzer for monitoring purposes. And if we go up further, stop here. And this is one of the things that we use. That's software-defined radio, which we will actually be using later today.
With Ben the things, she's going to find out what to. But you know, it's down.
Okay, thank you. Yeah.
At least you did what you are.
I'm not sure, was there a question or? Hello, can you hear me?
I think it was interference, Wolfgang.
Oh, okay. But you can hear me okay, I hope?
Yes, indeed. Yes.
Okay, that's fine. All right. So continuing up here, this is actually the instrument that we use most. That's a spectrometer. What that essentially does is we take in our 100 to 200 megahertz IF, the two polarizations, and that's then digitized on the fly. And on the fly, there's a Fourier transformation done. So we get spectra out of that machine. And depending on the mode of operation, it's either a high resolution spectrum with about 1 second resolution, or a lower resolution spectrum for pulsar work, where we go down in the temporal resolution. So this is one side. Then I move over to the second rack. Maybe start a bit here. This one is a fairly old rubidium oscillator. So this is our main clock unit, which delivers our 10 megahertz reference clock for all our instrument. Everything in here is tied to a reference clock. So we have reference clock distribution. This has something to do here with calibration signals. Here is a RF generator, which is the reference signal for our local oscillator. And then further up, actually there's not too much to be seen. There's a board here. This is a new digitizer board, which complements the one that I have shown before. This is more capable. It can run on 400 megahertz of bandwidth, and it's also faster in the time resolution. We're still configuring it and working on it. It's not operational yet. And above that, there's a computer that belongs to that, because this is giving us a very high data rate, and we need to make sure that we capture all the data. So this is the corresponding computer. And then we continue to the next rack. There's really not much of major importance here, because it's just computers, network switch, and in this case there are two computers. I have to say that the majority of our IT systems is not in the control room, it's in the basement, and the reason for that is a couple. They are noisy, they make heat, and also they generate RFI, so we want to keep them down. So the majority of our IT systems is actually in the basement. So I don't show that at the moment. It's just 2 racks of essentially 19-inch rack computers. All right, so this is our control room. Now let me turn that thing around again. And see that I adjust the camera a bit. Okay, at this point, I want to see whether there are any questions or any things of specific interest. So if you have any questions, please go ahead at this point in time.
Wolfgang, I'm quite interested in instrumentation and was wondering what technologies and systems you use for the positioning of the dishes. How does that hang together?
Okay, the one that I've shown in the racks, that's a let's see what's the English expression for that. I think it's SPC. It's an industrial control system that essentially does the low-level stuff, like making sure that you don't move the motors if the brakes are still on, that gears are switched correctly, and so on. This is very specific. If you move something with a weight of 90 tons with a couple of kilowatt motors, you want to make sure that you don't break things. So this is one side, which is specific because it's a large dish. Then the astronomical control, so moving the dish to the desired target position, that is done by a standard computer, which has an interface to our high resolution angular encoder. So we have 2 encoders on both axes, and they constantly feed the actual elevation and azimuth to the computer. And the computer then gives commands to this other system how fast it should move in this or that direction. So this has the actual control loop. What we do, obviously, what we need to do is to make a transformation from the astronomical coordinates to azimuth and elevation. So this is done in our PC. We're just using standard Python routines for that are readily available. So we have not written that. What we have written ourselves is the control system, which is specific to our instrument, like the speeds and how quickly the thing can move and this kind of thing. Does that answer at least part of your question? Or let me.
Yeah, that was really interesting.
Can I have a supplementary on that about what happens when the wind blows? How do you actually compensate for the wind loading on the dish?
Yes, we certainly have limits to that. What happens if the dish is pushed away a bit by the wind? Then obviously we get a signal from our angular encoders. They notice that, and then the power goes up to compensate for that. There are limits to that. If we have stronger winds, our pointing accuracy is less. We see some motion of the dish. We had that in the last couple of days when we had strong winds. And if the wind exceeds 12 meters per second, then we stop operating it because there are some, for safety reasons, there are some clutches which then would release the grip, and we would not be positioning anymore. And that's the rule that we have set ourselves, 12 meters per second measured at some place on our premise. Then we stop, we put it in birth bar position then, because that gives the least strain on the mechanics. But wind is something that is really a limiting factor. A bit about the pointing accuracy. When we move to a target, anywhere in the sky, we hit the target position by better than 0.1 degree, and we keep the position better by 0.05 degrees as long as there's not too much wind. If the wind goes in the neighborhood of, let's say, 10 meters per second, then we're losing pointing accuracy and we're going to 0.1 or 0.15. And beyond that, we just stop. Any further questions? If not, I will just move on and stop sharing this again. And let's see. For some reason, I have to go to this one again. Yes, okay. Now I'm back at my presentation. So let's have a look at the areas of observation that we do. This is just an overview, different areas that of things that we do. I've divided this in spectral observations and continuum observations. So spectral means we're looking at a specific spectrum. And obviously hydrogen is an important point where you have the classic emission in the Milky Way, then high velocity clouds, certain part of the Milky Way where we see, as the name says, high velocity hydrogen. Then something that is quite interesting, can only be done with a larger dish, is to see hydrogen in absorption against a stronger continuum source. Other interesting thing is hydrogen recombination lines. These are highly excited atoms that emit in the radio regime. Extragalactic hydrogen, so other galaxies, is something of interest to us. And then other things that are spectrally of interest are OH mesas. I'll talk a bit more about this today. OH absorption again. Other than hydrogen, one can also see carbon in recombination lines. And then I mentioned already that with the 10-meter dish, we do methanol mesa and water mesa. On the continuum side, where we look at the wide spectrum, they're sort of the static things like supernova remnants, H2 regions, or AGNs. But I have to say that we don't do much work here. This is sort of, I would say, of less interest to us. Maybe for other people it would be interesting, but it's not something where we do a lot of work. Where we do a lot of work is pulsars, and the special variant of pulsars, the Magnetars, and of course the famous fast radio burst. And another interesting thing is lunar occultations. We did that recently when a radio source disappears behind the moon. Some interesting effects go there. Okay, I can't talk about all of that, so I have selected 3 of that. It's OH mesas and magnetars and fast radio bursts. I've also selected this because most of our observation is now geared towards these 3 subjects. So if we look, what are we doing at the moment? These are really the 3 things that we do most. So I will start with OH mesas and a specific type of OH mesas, so-called circumstellar OH mesas. What happens there, the generation of these mesas, is you have a large infrared star, giant, supergiant star, something like that. And these stars, they emit, number one, strong infrared radiation. And the other thing that they do is they have an outflow of material from the star away. So it goes in away from the star as depicted by the green arrows. Now in this material, among other things, is OH. And what happens with OH if you have intense radiation, for some reason, sometimes my cursor disappears. Anyway, if you have intense infraradiation, the OH gets excited on a vibrational excited level and then decays. And on the rotational level of the molecule, it becomes, there's a population inversion, and that leads to an amplification, and at the end of the day, to a mesa. So what happens is that you have mesa emissions, and if you are, as an observer, where is my cursor again here? If you are as an observer here, you will see Mesa emission from the region that's moving towards you, and you see Mesa emission from the region that's actually moving away from you. So you would typically see a red shifted line, as depicted here, and a blue shifted line. So if you have a circumstellar Mesa, you will typically, of one sort or another, see such a double spectrum, double peaked spectrum. And the whole thing, of course, is shifted depending on the motion of the infrared star. Now, why is that of interest? These infrared stars, they are variable in a cyclic manner, at least during a certain time of their evolution. And I have depicted here a longer term observation on the left side where a special infrared star is monitored. It has been monitored by many years by the French radio telescope in Nancy. And these are the crosses. And we have taken over since 2018 observing that. And these are the rectangular markings here. And you can see from this, again, looking for my cursor. Yeah, okay. Again, we have here the two lines that you get as emission from this infrared star, or from the OH from this infrared star. We are running this observation program in cooperation with the University of Hamburg and the University of Manchester. They have doing that for many, many years. We have joined them in doing this observation and doing a long-term monitoring there. There are some interesting effects that can be seen. On the left side, you see one example where there's a star where the amplitude of this variation seems to decline. And this may be an indication that this is a transition from an AGB star to a post-AGB star. AGB stands for asymptotic giant branch. And this would be very exciting because so far the thinking is that it takes many hundreds of years for a star to do this transition, and this is something like a sudden shutoff, but it's too early to say something. We're also seeing something in the opposite, where we have an increasing amplitude of this variation, so reason unknown. So we just observe that and see what we can find out over the years. What I would like to do now is to show you to do a live observation of a Mesa. So what I will do is I will stop sharing this one. I will move over and share another computer screen, which I hope comes up. Okay, so let me explain what you see on the screen. This one here is our control screen. I have to say, we don't have any elegant clickable interface. I think everything at our place is command line. And this is our telescope control window. And you do enter a target here. In this case, I have already done that. So this is our infrared star where we want to go to. The telescope is stopped at the moment. And I will now just say go. And the telescope will start moving, hopefully. And I switch to the outside camera. So it's moving onto the target. Just checking when it has stabilized on the target. It will tell me that it has stabilized. Okay, now says tracking, and we are on target. Okay, so that is done. Next thing that we want to do is to do the actual observation. This is a window where I will start our spectrometer. And in this case, I'm using software-defined radio, just 6 megahertz of bandwidth in this case. And we do a 2-minute observation. I will just integrate for 2 minutes. That's what I will do. Hold on. I need to do one thing first. I have to tell our instrument that now we will be observing OH, which is at 1612 megahertz, not at 1400. So I have to switch our filters of the front-end amplifiers, otherwise we won't be seeing anything. So I almost forgot that, and I would have been embarrassed by not having any signal. So I have to tell them that our front end should go to OH. Yes, it has switched. So I restart the measurement now. And we have to wait for 2 minutes, roughly, before we can then collect the result. And we have then the opportunity to maybe answer some question now. So if you have any questions right now, please go ahead.
Wolfgang, I was quite interested in your list of different observation techniques to see hydrogen absorption. I'm being quite new to radio astronomy. This isn't something I've come across myself before. Can you, in 20 seconds, explain?
Yeah, the most prominent example is if you look at Cassiopeia A, which is a broadband source. Then between that broadband source, you have, between that and yourself, you have hydrogen, the different parts of our galaxy, the different arms of our galaxy. They are at different speeds. So you will see absorption lines in the broadband spectrum of Cassiopeia A. The point is, for amateurs who typically have a smaller instrument, like 3 meters or so, that's not visible for the following reason. As the smaller instrument has a wider beam, and the wider beam collects much more hydrogen, but the intensity from Cassiopeia stays the same. It's essentially a point source. So the relationship between the radiation from Cassiopeia and hydrogen gets much more in favor of the hydrogen, and therefore you don't see the absorption line. So it actually does take a larger dish to do that. I would say probably if you have an 8-meter dish, that should be doable then. Okay. In the meantime, the measurement has stopped. Gives some header information here that pops up. And what I'll just now do is I will read this file. We always record spectra in the so-called FITS format, flexible image transfer system or something like that. And my last observation is always latest.fits, so I don't have to remember those complicated names, and I just plot it. And as you can see, I already had a previous test done because I didn't want to be embarrassed by things not working, so I captured a spectrum just before our meeting today. So what you see here is the emission from around this infrared star. There's a double peak structure. It doesn't have always to be fully symmetrical, like in the example I've shown before. This is slightly different, where you have a broader emission, which is more redshifted, and this is a more blue shifted narrow line. As you can see, the whole thing is blue shifted, so it's in the star moving towards us with about, let's say, 55 kilometer per second. But this is what you would typically see from these infrared stars. This one is a fairly bright one, so you get a very clear signal with 2 minutes of integration time. There are weaker ones when we sometimes take an hour of integration time. And I should mention that it is doable to do a OH Mesa observation with a 3-meter dish. We've done that. The very strongest one can be seen, and not only we, but others have also demonstrated that successfully. So OH Mesa is actually something for somebody who has some experience with hydrogen line observation to do that as well, and I can certainly recommend it because it's again fun. Okay, I will now stop sharing from this computer and going here again, going back to my presentation. All right. So the next subject I would like to talk about are magnetars. Now, first let's discuss a bit what are magnetars and how did we come about observing them. A magnetar is essentially something very similar to a pulsar. It's a neutron star. And the difference, and that's why a magnetar is called a magnetar, it has a very high magnetic field. Now, even pulsars already have a very high magnetic field. And this one, a magnetar typically will have a 2,000 times stronger magnetic field. Magnetars are typically rotating slow, more than 1 second, a couple of seconds, not as fast as pulsars. And they spin down fairly quickly compared to pulsars, so they lose their rotational energy fairly fast. But again, fairly fast means in comparison to pulsars. Most of the magnetars are only observed in X-ray and in gamma ray. This emission is sometimes flaring. And only few actually are visible in the radio regime. And if they're visible, they have a very highly polarized emission and a fairly flat spectrum. As of today, there are only 30 magnetars known. So it's a relatively exotic object. And only from these 30, only a few, and you can name them one by one, are magnetars with radio emission. There's this one on top that was the first one that was ever observed in the radio regime. And then there are a few others. There's one which was only detected last year. And then there is a very famous emission from the one below here. There was a very intense emission. I think it was April 2020, or maybe a little bit earlier, when a magnetar, which was not known to emit in the radio regime, suddenly flashed with a very, very intense flash in the million Jansky range that was observed. And that, by the way, triggered, and we'll talk about it later, triggered the idea that magnetars may be eventually the same thing as fast radio bursts. Okay, the story of this magnetar, the first one known, is that it was discovered originally in 2004 as a continuum source. But then it was found somewhat later that it actually was a transient pulse radio emission. So it was very similar to a pulsar, but it was not detected directly. People saw it as a continuous radiating source, but looking exactly at it revealed that it was actually a pulsed emission. Then it was detected that it was highly polarized, and then this magnetar all of a sudden disappeared. in the radio regime. So it was observed for quite a while, a couple of years, but then it was just gone. Nobody saw it anymore. And this is a paper that describes that. Again, I'm fighting with my cursor. Okay, here it is. So initially, it was fairly bright, and then decreased, and then sort of meandered around, and all of a sudden it was gone. These dots here are observations that were tried, which were unsuccessful by various, by NOC, by Parkes Green Bank Telescope. They just didn't see it. It was gone. And then all of a sudden in December 2018, it was again noticed that this magnetar was back again in 2011. That was observed by the Jodrell Bank Observatory. And they sent out this astronomer's telegram, and we looked at it and said, okay, here's Jodrell Bank. They have 76 meters. They have short of 400 megahertz bandwidth. They integrate for 30 minutes. We don't know what their system temperature is. But they have a signal to noise ratio of 400. So if we take our parameters, we said we should see it with a signal to noise ratio of 31 within 1 hour. Maybe they have better system temperature, but we should be able to see it. And actually, we did see it. So this is a typical Presto plot. And you can see that is very clearly detected. Just like a pulsar, but it was a very clear detection. And this was after many years of silence of this. So, of course, this is interesting. So we continued observations. And while we were continuing observations, we also noticed occasionally a fairly bright single pulse. There's one example. There was a giant pulse on the 16th of December, so shortly after we made our first observation. So you can see this is without dispersion, so you see clearly that it is dispersed. And the red line is for comparison. That's the nominal dispersion line. So this is a nice detection. We continued, and without going into too much detail here, we did further observation, and we noticed it was getting less and less bright. So you can see a good signal to noise ratio here, end of December 2018. In March, it has become much fainter, and it sort of faded away. And we actually, we gave up observing that sometime later in 2019. And then we got a wake-up call mid of 2020, when somebody said, okay, it may have been faint, but now it's bright again. And they said, we're also seeing bright single pulses. This, by the way, was by, who did that observation? Yeah, that was in Australia with the Molonglo telescope. So they saw that it had become very bright. And of course, this made us interested in that guy again. And we observed it. And then ever since then, we're observing it. We sometimes see very, very bright pulses. This is a single pulse from this Magnetar, 640 Jansky. That is a very bright pulse. And what we're doing here is we continue these observations to see how that Magnetar evolves. By now, we have more than 630 hours of data collected. And what we are doing with this 630 hours of observation, we have a student working towards his master's degree, and he is looking into the data and analyzing the data, see how has it evolved, how is the relationship between these strong pulses and the average pulse. And especially what we are interested in jointly with other researchers is coming back to this idea, could magnetars eventually be the source of the repeating fast radio bursts? We have seen this one event by this magnetar in our own galaxy where it was very bright, but it's not clear, but this is the most favorite idea, that magnetars could be fast radio bursts, and this is the reason why we are doing so much observation there, so that we can see the details of the behavior, and so on. Okay, I will make a short pause again here to see if there are any questions before we move on.
Wolfgang, do you do the de-dispersion all in software? Because I didn't see any banks of filters or anything.
We do the software in, the de-dispersion in software. So what we are getting from our spectrometer is a spectrum with about, it's 168 channels, each 500 kilohertz wide. With a time resolution, depending on what we need for the magnetar, we use 218 microseconds. So we get every 200 microseconds, we get a spectrum. And then we collect that over a certain period of time. And then, of course, we can use the spectrum and the time of when the spectrum arrives to do the de-dispersion. And that's a later process that's done. It could be done in principle on the fly, but we are doing many observations where we don't know the dispersion beforehand, so we have to go through trial dispersions. For example, if we use a system to look for new magnetars or new FRBs or pulsars, and we do and search through the parameter space.
Right. Yeah. An interesting historical thing is Andrew Lyne was the first person at Jodrell to observe pulsars.
Yes, that's the famous historical finding when they were surprised by this pulse, and I think they didn't do de-dispersion because they didn't expect that, but they had a narrow bandwidth, and it was a pulsar with not so high dispersion. For example, if you take the strongest pulsar in the northern hemisphere, that one at 1400 megahertz, you can live without de-dispersion.
Yeah.
Of course, with this one, you can't.
Yeah.
It's fairly displaced.
Well, I always remember that when they observed the strongest pulsar, you could actually see it on the signal meters ticking.
Yeah, we do from the strongest pulsar. We do see the single pulses. It's not a pulsar that has what we call giant pulses. So every now and then there's a very intense pulse. The strongest pulsar has the typical variation of a couple of, let's say, factor of 5 or so in the variation. It also has a strong scintillation. That means that there are times when it's weaker and it's times when it's stronger. But to see it actually on every single pulse, yeah, you have to have a certain size of the dish. It can't be done with a 3-meter dish, but we can see it, yes.
Wolfgang, have there been sufficient pulses for them to be able to deduce a rotation rate?
For the magnetar, yes. Yeah, sure. I mean, when we go back, well, it's covered. The rotation rate is 5.542 seconds, roughly. It's slowly going down at the moment. Obviously, it's a little bit of spin down, but it's not fast spinning down. So it's fairly well known, the rotation rate, yes. Any further questions? Okay, then let's move on. Maybe before we move on, maybe it's a good time to do a second observation. Of course, I would have loved to show you the magnetar tonight. Unfortunately, it's below the horizon, so we have to wait until 1 o'clock in the night to get it, and I don't think we'll extend our session that long. But let's do a pulsar observation instead. move over to the other computer. Let's see, share my desktop and go over. Okay, the first thing that I need to do is we were observing at 1612 megahertz. We have to go back to the 1400 megahertz. So I will give a front end command for the hydrogen range. Just observe my spectrum. Yeah, it's coming up. So we are now back in the 1400 megahertz range. The reason why I could observe the pulsar also at 1600, but it's much more impaired by RFI, so I prefer to go to 1400 megahertz. Then we need to go to the target. Just give an abbreviated name. You can see that is the target. This is the strongest pulsar. And we move the telescope there. So you can go and watch the telescope move. So it has stabilized onto the target. And now I will record data. This is done by a program that will read our spectrometer. Our spectrometer is switched to a mode where we record the spectra with 218 something microseconds resolution. And I just need to say B for begin. And then you see the data counting up. So you have about a little bit more than 1 megabyte per second data recorded. And we just do it for 1 or 2 minutes. We'll wait for a minute or so. We now have recorded about 40 seconds. Just wait a bit more. Okay, now I will, while it's still running, I can already start looking at things. The first thing that I need to do is to reformat the file that we record into a common standardized format, which is called a filter bank format. Let's call that 29.1. That will be our filter bank file. So we just converted that. And then we use Presto, a program from Presto, to analyze the data. So we have 168 channels of spectrum. We know it's the PSR plus 55. This is a known pulsar, so we can say no search, doesn't have to do search for period, and our file is this one, and if we're lucky, we're seeing something. Yeah, that's the pulsar. So about a minute of observation. Obviously, this is the strongest pulsar, so it's a very clear signal. What you see, of course, this is the pulse. This is how it evolves over time. What is interesting to see here is the intensity over the frequency. So it starts here with 1330 up to 1430. This is our observation range, and you see that there's quite some difference in intensity. And this is due to scintillation. If I would do the same measurement, let's say in 20 minutes from now, it would look different. And this pulsar is very famous for that. It has a strong scintillation. The reason for scintillation is these are fluctuations in the interstellar medium. It's not like when you have scintillating stars, then it is the motion of our atmosphere. This is not the motion of our atmosphere. It's actually if you will, the motion of the interstellar matter. The electron density varies and things like that. Okay, so while we have been collecting more data, we can do the same thing again with more data. Essentially, the signal to noise ratio gets better over time. So this is the way we do our pulsar observations. Okay, let me just go and stop that. So by now we have collected several hundred megabytes of data, and you can imagine if we do this sometimes around the clock that we have we're collecting quite a number of data. We have about total of 300 terabyte of storage, and so we can keep for quite a while. We try to keep as much data as possible, but eventually we have to throw away observations if things get too much out of hand. Okay, questions to that? Okay, then I will move on. Let's see. Now I need to share that again. Okay. So let's move on to fast radio bursts. First of all, what are FRBs? From the phenomenon, these are single events, a single flash from an object, a single radio flash. What is striking about that is it has a high dispersion. The dispersion is so big that it cannot be explained by the Milky Way. So the thinking is that it is of an extragalactic origin. They are short, they are 1 millisecond. I'm saying here typical, maybe that's not quite correct. They are somewhere typically between 1 and 10 milliseconds. From these FRBs, there are 147 known so far. At least those are the ones that published as of April. And there are many, many theories what might be the origin of these fast radio bursts. They were originally thought that these are one-time events. Just something catastrophic happens, two neutron stars collide or something like that. But then one found that actually there are some which do repeat. So the same location, same dispersion measure comes again. And so now the question is, are the single FRBs the same type of thing as the repeaters, or is that something different? It was even known that, or is known that some repeaters have activity pattern in the sense that sometimes they're more active than at other times. And this is sort of being in a regular rhythm. Anyway, we have been interested in fast radio bursts for quite some time because it's such an interesting subject and matter of current research. So we were looking for some repeaters. The first repeater ever detected was this one here. And we did a joint campaign with Effelsberg where they observed on a different frequency as we did. But we didn't see anything at the time. But there's a paper published on that because our non-detection was giving some indication about the spectral behavior. Then we tried another FRB, which had the advantage of being circumpolar, so we could choose any time to observe it. And there were some events where we thought, okay, if we had seen them, we might have had a chance of seeing that. Then we're still doing an observation of a FRB, this one here, because it has a regular activity pattern. So we know certain times when it's more interesting to look. And we have also been doing blind searches where we were just recording data while the telescope was in parking position and just then analyzing that for potential FRBs. But we gave it up essentially because it was such a massive amount of data and so cumbersome to analyze that it was a no-go. Anyway, what happened is that there is a repeater with a famous name 2020-11-24A. That is the date when it was detected. It is known a repeater. It was detected by the CHIME telescope in Canada. Has a dispersion measure of 413. And what happened is that the CHIME people, they reported end of March that they have seen increased activity from that FRB. They recorded 6 events in the last week or so of March. They had a strongest one with a fluence of 5.5 Jansky times milliseconds. And later on, they observed 6 more, but this triggered our interest saying, okay, 5.5 Jansky millisecond, well, maybe that's sort of at the limit of our detection. We looked at the CHIME observation. These are the 6 that were reported in March. And I have to explain how that has to be interpreted. These are so-called dynamic spectra. So you see the pulse here. And the frequency of the observation in the CHIME case is 400 to 800 megahertz. And this is de-dispersed. So in reality, the different frequencies would come at different times. So if you would not de-disperse, it would be sort of a slant line as we've seen before, but it's de-dispersed, so you can see it here. And they have these 6 events. This is a bit of marginal here, but anyway. That was published, and then people got interested in it. And not only us, but other telescopes started also observing that. There was the Australian ASCAP. They reported something with a fairly high fluence. And this is their report. Again, this is a dynamic spectrum. You can see that the pulse does not appear over the full frequency range, only part of it. That's the pulse. Oops, now what happened? I have to share that again. And it starts all over again. Let's quickly browse through that. Okay. There were other reports from the big 500-meter telescope in China, where they had a number of bursts. Then Goldstone in the US, in S-band, they did not see anything. Very Large Array had seen something. Effelsberg tried at high frequency, also did not detect it. And we started, as soon as we had seen this astronomer's telegram, and we had 90 hours of observation starting end of March until the 15th of April. We had a few events where we said, okay, maybe not, but rather not, okay. But then we had this one here. This is fast radio burst extremely intense for our 25-meter dish with a signal-to-noise ratio of 85. Again, this is a dynamic spectrum, de-dispersed. So we were very, very happy about it. This is a comparison, non-de-dispersed. The line and the red line is the nominal, if we use the nominal dispersion measure. So it shows that it is clearly a astronomical signal because it's not a straight line, it's slightly curved, and that is what it's supposed to be because there's a quadratic behavior. So we analyzed it further. We saw that it has a peak density of 250 Jansky. That is quite a bit with 1.5 milliseconds. And from that, you can deduct further parameters. So we had the exact time of arrival. We determined the dispersion measure of that FRB. We just also determined the fluence. That is essentially the energy, the integral under the curve of the peak. And this is a very massive signal compared to other fast radio bursts. So that was very interesting. And of course, we also issued a astronomer's telegram where we explained and what we did and what we observed and what we observed, and encourage other people to continue observations. And of course, we ourselves also continued observations on that. And this is hot news. This is a very recent observation. That's the second one. And since this is recorded and will be on YouTube, I don't disclose the parameters yet because that's going to be in a scientific paper. What I can say is probably the most energetic FRB that has ever been observed. So that's a very strong one. That's our recent success on that. We have now a cooperation with some of the other telescopes, joint observations, and it's an extremely exciting thing. That's besides the Magnetar, which keeps us very busy at the moment. We're trying to collect as much observation time as possible. So this is what we're doing, and thanks for listening. I hope you enjoyed it, and I'm happy to answer all the questions that you might ask.
Thank you very much, Wolfgang. Wolfgang, with the fast radio pulses, is there any mechanism, any way one can determine the origin?
Yes, in this particular case, oops. Okay, just turn to this camera. Well, in this particular case, because there were many observations, and among other observations, there was one from the Very Large Array, and they were able to determine the very precise location. And at that location, there is a distant galaxy, and everybody is assuming right now that this is the galaxy where this thing sits. Whatever it is in this galaxy. And when you know what is called the host galaxy, in this case, you can determine the redshift of the galaxy. And from that, one can determine the distance. And the distance expressed in light travel time is about 1.4 billion light years. So it's fairly far away, not very far, but 1.4 billion light years is quite something.
Indeed.
And if you consider what we are getting in terms of signal from that, it's a flash that comes from far away and has this energy. That's quite something.
Does that distance and the galaxy in the target area, do they stack up with each other?
Don't quite understand the question. What do you mean by stack up?
Well, is that you've got a estimate of distance from the dispersion, and you've got an estimate of a potential galaxy for its home. Is the distance to the galaxy and the dispersion
there's
match,
one,
or?
Yeah, there's one parameter which is unknown. That's the dispersion of the host galaxy. And therefore, yes, it's in the ballpark, making reasonable assumption about the dispersion from the host galaxy. But that makes the distance estimates typically difficult if you don't have any host galaxy. If you just have the dispersion measure, you know very well what is dispersion from our own galaxy, because there are models of electron density, but then the host galaxy you don't know.
Wolfgang, is it possible, can you hear me?
Yes, I can.
All right, this is Anthony. Is it possible, I have a 3-meter dish, which is really nowhere significant to what you have. Is it possible to add 2 more 3-meter dish and hook all 3 in an interferometer to do any type of observations of the pulsars and magnetars and things like that? Is that possible?
I personally don't have much experience with connecting dishes to an interferometer. It's actually something that we want to do with our 3-meter and our 2.3-meter dish. The benefit, obviously, with multiple dishes in an interferometer is getting resolution. For pulsars, you want to have sensitivity. So what you would be getting is 3 times the collecting area, which of course helps in detecting pulsars. Yeah, I mean, probably I'm too less knowledgeable about interferometry. I'm at the very beginning of my learning curve there, so I probably have to get the answer be done by somebody else.
And one more question, the software that you're using. I noticed one time I correspondence with you, you mentioned that whether I was using Linux or Windows, I prefer to use the Linux, the software that you're using. Is that Linux based? And I mean, on the OS, but the software you're using running on that, is that something available for amateurs to purchase or build? Or?
Yeah, first answer to your question, all our machines are Linux. We have something like 27 machines around here, and they're all Linux. The software that we use, fortunately, is freely available. The institutions that develop the software make them available. That's done by the students that develop there. Typically, it's a PhD work or several PhD works that goes into there. For the pulsars and the magnetars and stuff like that, also for the fast radio bursts, we are using mostly Presto. If you Google for that, Presto is a package that is very well suited for that.
Thank you.
Wolfgang, it's very impressive, the variety of phenomena which you're looking at. So I just wondered how much observing typically gets done at Astropeiler.
Yeah, in the recent times we have we really do a lot of observing. I would say at the moment our telescope is running, it's a rough guess, 30% of the time. So on an average 8 hours per day, but it's concentrated more on certain days when people have time. And fortunately, we have some people who are eager enough for observations that they're now doing the Magnetar observations at this point in time. They actually, if I look upstairs above me, there's somebody taking a nap or trying to get some sleep because he will start observations of the Magnetar at 1 o'clock in the night. So the fast radio burst, fortunately at the moment, it's very convenient. We start observations at maybe 9 or 10 o'clock in the morning, goes into the evening before it settles, and but that will move into the night in the next couple of months, so it will be more challenging then.
So do you have an on-site dormitory?
Yes, we have rooms where people can sleep. Yes, we have a kitchen where people can eat. We have fridges. We have a dishwasher, so that's taken care of. Yes.
I hope you don't have a microwave oven.
Actually, we have two. We use it with caution. We know.
Wolfgang, with the fast radio bursts, I noticed on the frequency line there was some gaps. Is that instrumental or is that real? And what's the process? Is that understood even?
Let's bring that up again. Why does it? Something. I think I did something stupid. Okay, let me. I closed the wrong window, but hopefully I will be back again soon. All right. So you are referring to the gaps here. Yeah?
Yeah, the gaps in the observing frequency.
Yeah, and some brighter spots in here.
And some spots,
this is,
yeah.
Yeah, this is scintillation. That is the same effect as we have seen in the pulsar earlier when I did the measurement. So there's a scintillation effect by our own galaxy. It looks like I need to turn on the light. It's getting dark in here. So yes, this is a known effect and actually an expected effect, and also a sign that this is of astronomical nature, that you do see scintillation.
Right. Are there any more questions?
I think if I may ask, one of my problems is I just cannot imagine how you schedule all this different observation time and find these very small points of signals that are occurring very infrequently, and yet other stations have seen them and you don't know the recurrence period. I don't know how you schedule that in with all your main things. I presume you have some kind of committee, but perhaps you can enlighten me just a little bit more. Thank you.
Well, you're referring to how do we distribute our observation time, right?
Yes, that's right.
Yeah. Well, we are in a very fortunate situation, unlike any other telescopes, that actually we have more observation time available than or the instrument has more time available than we do observations. We're limited by the people that do observations. And yeah, we have every freedom ourselves. So we as a team, a small team, define what are we going to observe, what are the things that we find most interesting, and we don't have to apply for anything. It's ourselves that do that. So it's fairly easy.
Thank you.
There's not really a conflict that somebody says, I would like to do that, and another one said, I would like to do this. The point is that while we are a certain team of a certain size, but from that team, there are different interests. There are people who are more interested in the technical side of things, maintaining the telescope, caring for the IT stuff, and so on. And then there are other people who are more interested in the physics sides of things. And typically, physics will determine what observations do we do. And therefore, it's really, for us, fortunately, it's a non-issue.
Yes, thank you very much.
I guess that's quite a unique situation. Are there any more questions? Okay then, Wolfgang, thank you so much. That was just fascinating and absolutely wonderful. And thank you for sharing your experience and observations and some of the instrumentation with us this evening. That was great. Thank you.
Well, thanks very much. It was really my pleasure.
Moving on, last weekend, Paul Hyde led a workshop on Spectrum Lab, and one of the techniques that he was talking about was SIDs, the sudden ionospheric disturbances. And then, amazingly, he arranged for some wonderful events in the afternoon. Now, Paul was going to share some of his observations with us, and maybe how he arranged for the flares, because I just want to know. Paul, over to you. You're mute, by the way.
No, yes, I'm okay now. So it's just a matter of finding, I've got too many screens open. Let's try that. Okay, is that coming across?
Yes.
Yes, good. Let's just, well, this is a bit sort of surreal going from one end of the electromagnetic spectrum to the other. And from one level of difficulty to the other. So thanks again to Wolfgang for such a great talk. Yeah, luckily I've been to Stockert a couple of times, so I appreciate the layout and everything. Okay, so just 3 slides, that's all, because it just happened to be coincidence. We are at the start of the next solar cycle. It's been very slow building, but we had a bit of activity last month, and we've had a bit of activity at the start of this month. And so no secret arrangements or anything, just pure luck. I thought I'd just show one slide of a quiet day. So this is 24 hours. We've got the hash from the various VLF transmitters, very low frequency transmitters, during nighttime conditions in the early hours and in the late hours. We have the chaos of sunrise when the solar radiation is hitting the ionosphere at all sorts of strange angles, including from the underside. So that's all very chaotic. And then the other notable thing here is this dark blue line here is a VLF transmitter on the East Coast USA, and therefore the sun is rising several hours slower. So that's why everything is time shifted to the right for this blue line here, which is very convenient because it extends the hours of viewing late in the day. So that's the sort of quiet day. This is my induction hob. You can see when I had my meal here. So this is this plus the very noisy nature of some of these signals is a reason for getting the receiving system out of the house and down to the bottom of the garden when I can. Other glitches, you can see local interference, obviously a bit of transmitter maintenance or adjustment at this point. That's certainly not a natural diversion. Okay, so that's the sort of background. And then on the day of the workshop, this is what we had. So this is the whole day at the top, 24 hours. And I think the thing I wanted to just highlight, it's very easy to see these SID events. Characteristic shark's tooth, or shark's fin rather, shape for the smaller and medium-sized ones. For the really large X-ray flares, then that breaks down, and it goes everywhere. But anyway, for now. So, and then these are just blow-ups, which I use to make the measurements for submission in the monthly reports. So that's this one is this very small event here, just coming out of the morning sunrise fluctuations just after 6 o'clock UTC. This is the midday one here, and then a couple of late afternoon events. And then it actually did it again the next day. So this is on the Sunday with a very large event. And since then, it's all gone quiet again. So that's I'll wait to see how long it takes before we get some more. And as I say, I for the SID measurements, I just take the start time, maximum deviation, and end time for submitting to John Cook, who compiles a monthly report from different observers. Right, that's my bit. Any questions?
Paul, did you see any effects of the CME that hit us on the 26th? Because I didn't see anything at all this time.
I'm afraid I haven't had a look at the 26th yet, but I will do that this evening now that you've piqued my interest.
Yeah, because when the previous CME hit, I saw it on the Iceland path on 37.5 kilohertz. But this time, the magnetic effects seemed slightly less disturbed than the previous one, but I saw absolutely nothing at all on 37.5 kilohertz. On the 26th, I just recorded 4-week SIDS, and that was it. The rest of it was just nothing at all. So that was really strange.
Yeah. I mean, for those who don't know, Mark has done a lot of work monitoring this Iceland VLF transmitter here, which displays uncharacteristic, or rather a behavior that the other VLF transmitters don't. Any other questions? Then I shall stop my share.
Yeah, I'll just say one other thing is that there's the partial eclipse of the sun on the 10th of June. So that would be interesting just to see if you can see the effects of the reduced solar radiation on that day.
I've got a question, Paul, possibly for Mark as well. On the 23rd, I saw on 23.4 kilohertz, I actually saw the SID just before midday as a downward going event. The ones on the previous day on the 23.4 were seen plainly as upward going events. I was surprised on 2 consecutive days to see so much, to see them actually reversed like that.
Yeah, well, the direction, basically you're looking at the result of 2 signals, one via the ionosphere and one via the ground wave, and that is representative of a change in level in the ionosphere. And really Mark is the person, because Mark's done quite a lot of work on modeling the height of the ionosphere through these sort of occurrences. Mark, do you want to say something?
Yeah, I mean, it really depends on what the height of the ionosphere is before you get the SID. And it depends on whether you're if you think that during the day the height lowers, so it's lowest at noon. If your flare comes before noon, then it will reduce the height. So the effect you'll see of the SID is the same as the effect you see during a normal day when it goes towards noon. I'm not describing this very well. But,
no, I'm following you quite well, actually.
If the if the flare comes when you're on the way up towards noon, then if normally at noon you see a high signal, the flare will go up. But if the flare comes, say, at noon, then it will go down because you're at, you know, it depends on the phasing. It's difficult to describe in a hand waving manner, but.
Thank you.
Any more questions on the SID events? I know some others at the workshop were really delighted and surprised at getting some data so soon, having set up Spectrum Lab. I don't think they're with us this evening though, but it was good, very good training session. So unless anybody has anything else to contribute tonight, can you indicate now? No. Okay. I will close the meeting, and we will we'll gather again next Saturday for Python, and in June with Peter East on the tricky question of pulsars. Great. Good night, everybody. Sleep well, and until next time. Good night.
Good night.
Good night.